Okay, hello everyone. Welcome to this Syrris webinar. My name is Leandro Carvalho, and I'm going to present you today this spotlight on flow photochemistry. So before we start, I would like to give a brief introduction to Syrris. So Syrris was founded in 2001 to cope with some demanding technologies from the pharmaceutical company. And now we are the longest established flow chemistry company in the world, and the only company to address both batch and flow chemistry markets. So among our customers, we have the top 20 pharmaceutical companies and the most leading academic institutions. So we are here in Royston, where we have two manufacturing sites, including this glass manufacturing, and we have global sales and support offices. So in 2020, Syrris was acquired by AGI Group. So the Asahi Glass plant is headquartered in Japan and have some subsidiaries in UK and the US. So AGI is the world leading in this glass manufacturing technology, and now we have this wonderful synergy between Syrris and AGI with this highest performance and precision glass manufacturing and this easiest to use and superior design of the Syrris systems. So after this brief introduction to the company, I would like to do this glimpse of introduction on photochemistry. So how can we initiate a chemical reaction? Well, there are many ways to initiate, but the most common in general, the chemical reactions are initiated by thermal initiated. So we have to give some heating. Sometimes we have to cool it down. And but there are some lesser used methods. For example, electrochemistry, where we are going to use electrons, or photochemistry, where these reactions are triggered by the incidence of light. So these less common methods are increasing trend in these recent years, and sometimes they are referred as reagentless chemistry. So, and one of the key advantages of flow chemistry, for example, is to make these methods, these lesser used methods, to make them easier to do. So in the range of Asia equipment, we have the Asia Flux module, which allows us to perform some continuous electrochemistry, and now we have as well this Asia Photochemistry Reactor, allowing us to perform some continuous flow photochemical reactions, enabling the widest range of applications and versatility. What is photochemistry? So basic photochemistry is the branch of science which is concerned with the chemical effects of light. For example, in nature, this is the basis of the photosynthesis, and I would say is the basis of life, in fact. So we have this associated with some process in our bodies, for example, the vision, and in the formation of the vitamin D with the sunlight. Photochemical reactions proceeds differently to the other techniques, so giving us access to unique chemistry, so unique products that is always referred as cleaner and therefore greener methods. If we think about the light as a renewable resource. So how this works? So when a molecule absorbs some photons, some energy, there is a change on the electronic structure, and then this molecule can react to themselves or with other molecules. So, and the incidence of this light, of this energy, proceeds in a very specific way. So each molecule will receive some specific degree of energy, specific wavelength, and will produce specific products. So after that, I would like to give you some historical aspects of this organic photochemistry. So this is not a new topic. So this interaction of light and chemical compounds were observed since the 18th century. For example, here we have this. I think is the first thing was published, and they observed this sesquiterpene, the alpha santonin, became yellow, and then exploded upon it was exposed to the sunlight. So later was explained this process is a sequence of three chemical reactions. In this case, photochemical reactions, which leads the product number 4, and this bursting effect was attributed to this large change in the crystal volume on the dimerization. So there are some exciting and remarkable examples of the application of photochemistry to make some organic compounds, to apply in organic synthesis. For example, we have the synthesis of cubanes in 1964. Corey used this retrosynthetic approach and the photochemistry to synthesize these caryophyllenes, and as well Wender 1981 with the synthesis of cydrine. So here I would like to point out about the increasing of complexity. So here we can see from relative simple compounds applying this kind of photochemistry, we can have some really complex molecules. So which will be, I would say, not impossible, but it's very hard to do if we not use this kind of synthesis. So how it's developed? So why use photochemistry and flow chemistry? So we as a chemist, we all know some of the benefits we have using flow chemistry. So we have the precise control of some reaction parameters. For example, we have better control in the temperature, mixing, stoichiometry, and reaction times. When we put together photochemistry and flow chemistry, we can add some more advantages, some more benefits. For example, we will have some improved irradiation of the reaction because the light will be transmitted. This transmission of light will be better through this microcapillary, which is generally used in flow chemistry. We will have some improved reaction scalability, so it's easier to increase the light power, enabling more photons to actually trigger the reaction. We will have some more improved reaction selectivity using these single wavelength LED light sources. We will have some improved reproducibility because we will have this control of exact control of the reaction times, and we will have like will have over irradiation, which is pretty common in batch, for example. We will have some improved mixing and heat exchange, and we will have this ability to perform like multi-phase chemistry, and it's pretty easier to pressurize flow reactors in comparison with batch. So we can use some gases for the reaction, and then on the top of this we will have some increased of safety because we can construct our flow reactors, shield them, and then we can put some interlocks, so we will prevent this exposure of this high intensity light. Talking about some kind of photochemistry light sources, this is very nice. So you have a light sources inside you into a molecule and trigger the reaction. But there are some problems. So historically, photochemistry has utilized this kind of high intensity and high power mercury lamps. And the problem with this kind of light is they produce a broad spectrum of wavelengths. So that selectivity that I mentioned before is almost lost because you are inciting this light in a very broad wavelength and don't have this selectivity. And on the top of this, they produce a lot of heat as well. So almost always this required external cooling to keep the temperature of the reaction in low temperatures. So, but now we have the advancing of this LED technology. So now we have this high intensity power LEDs with a narrow emission band. This allows us to be more selective, so to give more improved reaction times, for example. And we have these LEDs as well generating more or less heat. So it's not always required this external cooling. Here is just a comparison with the low, medium, and high pressure mercury lamps and this broad range. So, and we have these UV LEDs and visible LEDs, which we have as well covering all this range, since from the UV up to the red in this case. Talking about some the photochemical reactors itself, there are another problem with this incidence of light. So the problem is they lose some energy very quickly upon the molecules are going to absorb this light. So for example, if we have a vessel, only the surface of this vessel will be irradiated. So because the light will not be transmitted through this reactor, and we will have non-uniform reaction conditions. So if we are going to microcapillary, which is applied very well established in flow chemistry, for example, we will have full transmission of this light, and this will give us more homogeneous irradiation and giving us shorter reaction times and less side products. This is the main reason for this perfect partnership between photochemistry and flow chemistry. And then thinking about scalability, so for the same, as I said before, the same problems we saw for the transmission of light, we have here as well. So it's not simple just to increase the vessel size and, for example, double the volume of the reaction. So we will have some problems with the light transmission, and the reactions will not proceed just like we would like to proceed. So, but with flow chemistry, we can increase the throughput just simply running the reaction for longer times, or then we can increase the number of reactors, putting them in series or in parallel, and then we can use the same reactor and increase the radiant flux, for example, adding more LEDs modules. And then we will have some reaction scalability. Well, until here, I talked about photochemistry and why this is important to use with flow chemistry. So now I would like to talk about some modern examples, some selected examples about the applications of this flow photochemistry. The first example that I would like to talk about is halogenation reactions. So as we know, brominated compounds are common building blocks for organic synthesis. Some of us, for example, use this daily basis in the lab. So the substitution of a hydrogen atom for a fluorine or, for example, 3-fluoromethane has a strong impact on the properties, the physical chemical properties of the molecules. And this is very important parameters for the pharmaceutical industry, for example. So the first example is coming from this group in Australia and deal with this continuous, the photobromination using N-bromosuccinimide. So as I said, the scaling up, especially in industrial environment, is still underdeveloped because the main reasons I've mentioned before, we have these limitations with the Mercury lamps because they use high amounts of energy and generally furnish low yields and a lot of undesired side products because of the poor transmission of light. But as I said, the need for access these RR bromides, for example, is still there. So in this example, the authors describe a methodology to scale up this process for the benzylic bromination. And they used this activation LED technology for activation of the compounds and NBS, N-bromosuccinimide, as a bromide source. So here is the optimization. So after they did the optimization, for example, on the temperature, residence time, solvent, and the wavelength, they could find 90% yield and excellent 97% of selectivity for the monobrominated product. Expanding the scope of the reaction, so they could obtain those examples with a reaction scale of 10 millimoles is roughly 4 grams, with residence times up to 10 minutes, yields up to 99%, with some productivity of up to 94 grams per hour, and this space-time yield 2.35 kilograms per liter per hour. The next example comes from the tin oil group. This paper was published in 2014 and uses this photo Redux catalysis to proceed the 3-fluoromethylation and the perfluoromethylation of some heterocycles. So as I mentioned before, the incorporation of fluorinated moieties into the chemical compounds can bring several advantages. For example, we can improve some of chemical stability. We can modulate some important properties for the pharmaceutical, for the agrochemical, and for the materials industry. So in this case, the authors describe this approach for a photocatalytic 3-fluoromethylation and perfluoroalkylation of these heteroarenes in continuous flow. So here you can see the fluidic network. So they have the reagents being pumped, and they use this 3-fluoromethanol iodine, which is a gas. So they use a mass flow control to dosing this reagent, and then irradiated this with blue LEDs in a microreactor. So they have some kind of a reaction optimization where they found using this ruthenium-based catalyst 1 mol%, 2 equivalents of base, acetonitrile, and the irradiation with the blue LEDs. So after the reaction optimization, they found that the TIMIDA proved to be the most effective for this, and they used it for equivalents of these gas reagents. And after a residence time of 8 minutes, they could find 99% of conversion, 95% yield. Expanding the scope of the reaction, they could find, produce 12 examples of this trifluoro methylation with yields up to 95% and the residence times of 32 minutes. And for the compound 2D, they could obtain this in 2 gram scale. So in a further optimization, they use another reagents to perform the perfluoroalkylations. So here we can see these 5 examples. In this case, they could use up to 0.5 mol% of the catalyst and obtaining yields up to 95% and residence times of 20 minutes. In a sequential publication, they did apply the same methodology, but now they used another catalyst, is a metal-free one. In this case, they use this eosine, and this is good because in this case can bring some advantages. For example, it meets the strict product regulations for pharmaceutical industry, for example, avoids some expensive purification, and then provides a more cost-efficient alternative because, as we can see, the price for the catalyst eosine is less expensive comparing to the metal-based one. And here is the example. So they could obtain 6 examples with yields between 30 and 99%, is comparable with the yields they obtained before. And here is just a batch comparison showing us some advantages of using this methodology. So the next example is about the light-inducing cross-coupling. So the cross-coupling reaction is very important for the formation of carbon-carbon bonds, and generally we have some kind of organometallic reacting with some kind of halogenated compound, and then we will need some kind of catalyst and ligands to obtain the cross-coupling product. And in this case, some kind of light irradiation can be beneficial. For example, increasing yields and even the selectivity of this reaction. So this example comes from the research group of Jesus Alcázar from Janssen in Spain. So this is an impressive proof of this straightforward combination of a continuous flow synthesis and using solid materials, for example, metallic zinc, and this light-induced cross-coupling reaction. So just showing in more details, the main point here is the formation of the organozincate number 6 from the compound number 5, passing it through a column of activated zinc, and then reacting direct with the compound number 7 in that photoreactor irradiated by blue LEDs. So after 6 hours of processing, they could obtain about 20 grams of the product. And of course, they tested in absence of light, and this yield was very low. The next example is about photooxygenations. So to proceed with photooxygenation, we need to use this singlet oxygen, which is obtained from the ground state oxygen, which is a triplet oxygen, by the irradiation of light in the presence of a suitable photosensitizer. So here we can see this nice photocatalytic cycle. So we have the photosensitizer being activated by visible light, and then transferring this energy to the ground state oxygen, and then forming this singlet oxygen. And here on the top right, we can see some common utilized photosynthesizers. So this example comes from Brazil, from the group of Professor Rodrigo de Souza, Rio de Janeiro, and Professor Kleber and Tim Broxson from UFSCar. So here they applied this photo-oxygenation for obtaining some key intermediate for the synthesis of cannabinoids. And as I said, they applied this photo-oxygenation to limonene. So the common approaches to obtain this kind of products involving the coupling of this key intermediate, number one, which is para-methanodienol, and with the correct phenol. So although the most of the routes are described as like ready available, there are some, again, problems with the synthesis of this in large scale. And generally, the literature points that the lower yields, for example, 20%, and some problems with the selectivity, and also using some large amount of oxidants, and with longer time reactions and low atomic efficiency. Here the authors used this photosensitizer, this formation of the singlet oxygen, and reacting this in situ to the photo-oxidation of the limonene and obtaining the desired product. So this meets some principles of the green chemistry, for example, atom economy, and reduce this releasing or exposure to the environment to dangerous substances. Here is the fluidic setup they've used. So they pumped the limonene, the mixture of limonene and TPP, which is the porphyrin, and used this tubing tube technology to saturate this reaction medium with oxygen, and used this 1 ml microreactor and some white light, 100 watts LED white, and obtained the desired product. So after some 20 minutes of reaction, it was possible to get 99% of conversion and 48% of the desired product. And here is the beauty of this kind of technique, because they just changed the white light, which is a broad emission spectrum, and now they used some blue lights, the same power, 100 watts, and then they observed both conversion and productivity values were increased. And here, now they changed the volume of the reactor from 1 ml. Now they changed it for 30 ml reactor, and improved some more blue lights. So improved the power of these LEDs. And after all, it was possible to get 44% of conversion, 55% of selectivity, and the productivity was increased by 200-fold, which is quite impressive for this kind of reaction. The next example is this late stage CH activation or CH functionalization. So this is a very valuable tool in modern drug discovery, because there are there are few methodologies that can proceed this kind of a reaction. And the photocatalysis is one of them. So here is just an example of this technology, of this CH alkylation. For example, we have this compound phasodil, which is an API and is a potent vasodilator. And they've used some kind of organic peroxides irradiating with blue lights, using some kind of photocatalysts, cetonitrile and trifluoroacetic acid, and they could obtain the methylated, ethylated, and cyclopropanated products from moderate to very good yields. The last example is one of this increasing complexity. As I mentioned before, this technique is excellent to get the complexity increased. So for example, here we can see this carboline being reacted with some kind of acids using this visible light and some kind of catalyst. And we can obtain, like you have to 1, 2, 3, 4, 5, 6. The product has 6 6 rings. So this is a quite impressive increasing of complexity. And we have featuring in these higher product yields compared to batch, and the shorter reaction times, again compared to batch as well. So now I hope I could give you some glimpse of this technology, photochemistry being applied in flow conditions. And now I would like to talk about just giving an introduction to the new Asia Photochemistry Reactor. So the new chemistry photochemical reactor enables us to perform continuous photochemistry and do some applications just like we saw before. So the photochemical reactor can be used with a range of the range of the Asia products, or you can use this together with another system you may have in your lab. Just would like to highlight some kind of specifications of this reactor. It can house up to 8 LED modules. So it can be fixed wavelength, or it can be mixed wavelengths or blank modules. So we have a full range of monochromatic LED modules. The output of this, the output power ranges from 3 watts up to 108 watts. This is the output. Reactor, the reactors can be 4 ml or 16 ml. When using with a range of Asia products, we can precise control the temperature between -40 degrees up to 80 degrees. And of course, this module is completely interlocked by safety. Here, I just would like to point out some of, I think, is astonishing characteristics for me. The possibility to use multiple wavelengths in the same reactor. And remembering these LED modules were designed to not, there is no need to an external cooling source for example, circulators. So this is a big advantage as well. So this opens the possibility for the chemistry to explore new and exciting areas of photochemistry. So I will finish here. Thank you very much for your attention. And now I am open for the questions. And please feel free to type in the chat box, or if you want, you can send us an email. So I will ask Andrew now. Andrew is here, and could you read some of the questions for me?
Yes. So I've got a question here. In the photo oxygenation introduction slides, you showed a range of photosensitizers. What are the advantages of using different photosensitizers?
Oh, yeah. Depending on the wavelengths you may have available for the photochemistry in your photochemical system, you can select the correct photocatalyst. For example, that one which was used, the porphyrin, I think the absorption, the major absorption band is about 420 nanometers. So the blue LEDs is about 450 nanometers, the emission. So you have to match this light emission with the absorption of the photocatalyst. So if you have, for example, want to use another wavelength, you can find the catalyst, the photocatalyst that match with that wavelength.
Thanks. Another question here. You showed examples of using with introduction of the gases with both mass flow controllers and tube-in-tube technology. What are the advantages or disadvantages of each?
Okay, in the first example, where was used that mass flow controller to input some gases, there was a need to measure, to dose that kind of a reagent. And in the second case, for example, which they use that tube-in-tube technology, so the membrane diffusion, there was no need like to actually measure the quantity of oxygen. So they were concerned only just to saturate the medium. And in this case, for example, the tube-in-tube technology, there are some kind of limitations because as long as I know, we can use just linear gases and in very small quantities. If you go for like bigger atoms, bigger gases in volume, that you will find some problems with this diffusion through that PTFE tubing.
Okay, another question here. Without applying external temperature control, what's the average temperature achieved with the incident of the LED lights?
Okay, the average temperature when you are using 4 LEDs modules, so our reactor can house up to 8. So if we use half of them, is about 30 degrees. And this is at 100% power. And if you use full LEDs like 8 at 100% power, the reach temperature is roughly 50 degrees.
Okay, thanks. Got a question here on the material of construction of the reactor.
Oh, the reactor is the same as as we have here. So is PTFE PFA reactor, and the external parts there are some glass and PTFE connections. So the reactor itself is the same as usually for the range of Asia products. And what we did here was to have an adapter to house these LEDs. So we can use this to just slide the LEDs. So actually the reactor is PTFE and is the same as the range of Asia. And then we have this ring, which has this adapter, and then we have the LED modules.
So I guess that covers, and there's a follow-up question here about light transmission. The material of construction is more than adequate for transmission of visible light.
Yes, there is no problem for transmission of the visible lights. It's a PFA, and this is quite transparent to even to some kind of UVA, I think.
Okay, I've got time for probably another couple of questions. Bear with me, I'm just reading through these. Have we tried to perform some process intensification during our tests? How many hours has it been worked continuously for? And is it possible to work on a gram scale?
Okay, the question is very good one. So we didn't try yet some kind of process intensification, but we have tested the lifespan for the LEDs, and we are counting now more than 1,000 hours for this continuously processing, for example. And yes, the second part is the grams.
Yeah, can you operate on a...
Yes. As I said, we have two volume sizes, so 4 ml and 16 ml. And this is enough to, as I said, if you let the reactor, depending on the reaction, if you let the reaction running continuously, you can easily get some decagrams or even 100 grams of this product.
And I think I'll take another couple of questions on here. This one looks like from a current Asia user. Can we use the same modules, like the heater and the one on the left, and only change the reactor adapter, or do we need an entirely new module?
No. This Syrris Asia Photochemistry Reactor was designed to sit, as this customer said, into the Asia heater. So if you want to control the temperature like 8 degrees, up to 8 degrees, you can use this in conjunction with the Asia heater. On the other hand, if you want to cool it down, it can sit as well in the Asia cryo controller, which we have just these adapters that will allow us to assembly the Asia Photochemistry Reactor in our modules. So there is no need to buy like a new module, only the photochemistry reactor.
Thank you, Leandro. I think as we're running to schedule now, there was one last question here about an explanation of the reactor. What I would like to offer for people on the call, if you'd like to find out any more information, then contact us at Syrris.com,
yeah,
or drop us an email at info@Syrris.com, and we can discuss this further. So I'd just like to say thank you to Leandro.
Thank you very much. Thank you very much all, and for joining us today, and see you in the next webinar. Thank you very much.